Let's look at this problem. From a regular octagon, a triangle is formed by connecting three randomly chosen vertices of the octagon. What is the probability that at least one of the sides of the triangle is also a side of the octagon? Obviously, this is a probability/counting problem. For such problems, there are usually many kinds of solutions depending how you build your mathematical model. In this video, we are going to share two solutions. One way is to count the number of such triangles directly. And the other way is to count the number of triangles that do not satisfy this condition. And we call that an indirect way. Okay, let's look at the first method. In the first method, since we are going to count such triangles directly, let's analyze the conditions. The condition says at least one of the sides of the triangle is also a side of the octagon, which means these two shapes have at least one common size. Therefore, it's a natural way to subdivide this problem by this criteria, the number of their common size. All right, let's look at the first scenario. In case 1, in this scenario, let's consider these two shapes, the triangle and the octagon, have exactly one common side. So let's call that one common side. And in the second scenario, let's consider the case that these two shapes have exactly two common sides. Let's call that case 2. And they have two common sides. All right. Do we have a case 3 such that all the three sides of the triangle are sides of the octagon? No. If you give it a try, you'll find out that such triangles do not exist. Therefore, we only have two possible cases. Then this problem is subdivided into two slightly easier problems to handle. And this is a typical technique when you deal with counting problems. All right, let's look at the case 1 first. In case 1, since they only have one common side, then let's start from there. Let's first assume the common side is this side. This side, I highlighted here. Let's say this is the common side. And then immediately we know that this side gives two vertices of this triangle, right? These two vertices are, of course, vertices of the triangle. Then the rest of the story is to determine where the third vertex is. And we know that an octagon has 8 vertices. Therefore, the third vertex of the triangle got to be from one of the remaining 6 vertices. So let's mark them as 1, 2, 3, 4, 5, 6. So these 6 are the remaining 6 vertices. And let's look at 6 first. Can 6 be the third vertex of this triangle? No, because in that scenario, this side will also be a common side of the two shapes. And that obviously contradicts this condition, one common size. Therefore, the vertex 6 is out. And similarly, vertex 1 is out as well. Then the third vertex of this triangle got to be from the remaining 4 vertices, from 2 to 5. We have 4 choices. But we are not done yet. This is because the starting common side, this side, that's randomly picked. This side does not have to be the common side. It can be any of the 8 sides of this octagon, right? This can be the common side as well, and this can be the common side as well too. Therefore, there are 8 ways to choose this common side. Then the total number of cases in this scenario is 8. So we have 4 times 8. That's the number of all possible triangles that only have one common side with the octagon. In case 2, we'll consider the scenario that the two shapes have 2 common sides. Then a good starting point is these 2 common sides are adjacent. For example, these 2 common sides. Right? These 2 common sides are adjacent. And the 3 vertices are determined as well. Right? Let's call this A, B, and C. I'll clean up this area a little bit so we can see it clearly. Alright, then we connect A and C. That's our triangle, right? It's a good triangle that satisfies we have 2 common sides. Good. But what if these 2 common sides are not adjacent? They are separate. What if one is here and one is here? What if it's these 2 common sides? Then immediately we will realize that these 2 common sides determines 4, 1, 2, 3, 4. Determines 4 distinct vertices. At the same time, we all know that a triangle only has 3 distinct vertices. Therefore, that's not possible. Then the rest of the story is only to count in how many ways we can select 2 adjacent common sides. In order to count that, let's pay attention to this point B. This middle point, or the middle vertex. We can think of this B as the pivoting vertex, because as long as we determine this pivoting vertex, then the adjacent sides are determined. Any pair of 2 adjacent sides is uniquely determined by this pivoting vertex. For example, this one, I'll change color. I'll use pink. Let's look at this pair, right? These 2 are a pair of adjacent sides, and it's uniquely determined by this pivoting vertex. Therefore, how many pivoting vertex we can choose from this octagon? This octagon has 8 vertices, and each vertex can be this pivoting vertex. Therefore, we have number 8 many choices. 8 is the number of all such triangles that have 2 common sides with the octagon. When we sum these 2 numbers up, we will get all the number of triangles that have at least 1 common side. Okay, then how many triangles can we build from 3 randomly chosen vertices? We have 8 vertices. So randomly chosen 3, that's 8 choose 3, right? And then the probability is 4 times 8 plus 8 divided by 8 choose 3, right? And that equals, we don't want to compute the final results of the numerator because there are a lot of products on the denominator, so there could be some cancellations. Therefore, let's factor this 8 out, and then times 4 plus 1, that's 5. And the denominator equals 8 factorial divided by 5 factorial times 3 factorial. To simplify this, we'll multiply 3 factorial on the top and 3 factorial on the bottom. So we cancel these 2 3 factorials. We cancel this 5 factorial with this 8 factorial. And then we have 6 times 7 times 8 left. Therefore, this equals 6 times 7 times 8 on the bottom. And then on the top, we have 8 times 5 times 3 factorial. This 8 cancels with this 8. 3 factorial is 6, cancels 6. Therefore, the final answer is 5 over 7. Let's look at the choices. D. D is 5 over 7. That's our answer. Alright, so this is the direct way to do the counting. Now let's look at the second method, which to do the indirect counting. Alright, let's browse down a little bit to have some space. Okay, so that's method 2. So this indirect way may be slightly complicated than the direct way in this problem. But it shows some interesting technique that I really want to share with you guys. Anyway, let's get started. Let's draw a simple diagram of this octagon. So let's say this is our octagon. And I will highlight these vertices. So I will highlight these vertices for a better view. Now, what we really want to do is to count the number of triangles that have no common size with the octagon, right? That's what we want to do, and this is the flip side of octagon. That's the flip side of this story. And how many such triangles do we have? Alright, in order to do that, since we don't have any common size now, so we can't start with a common side, then what should we start with? Then an obvious choice is to starting with a vertex, right? A common vertex. Alright, without loss of generosity, let's assume this is the first common vertex or chosen vertex for the triangle, right? This vertex. Now, the rest of the story is to determine how do we select the remaining 2 vertices for the triangle. In order to simplify the problem, let's just consider the selection in one direction, right? Let's just consider that in the counterclockwise direction. You can certainly choose the clockwise direction. That doesn't matter. By symmetry, they are equivalent. If we choose the other 2 vertices in this direction, we can eliminate one vertex right away. That's this one. This one. This vertex is out because we can't have 2 adjacent vertices for this triangle. Otherwise, we will have this common side, right? So that's impossible. Therefore, the remaining 2 vertices for this triangle gotta be chosen from the rest of the 6 vertices. So we have 6 remaining vertices, right? So vertices. We gotta choose 2 vertices out of the 6. Good. Now we'll build a small and interesting mathematical model. So let's look at it. Before that, I want to point out that some students may ask, why don't you kick this point out? The very next point to the chosen vertex in the clockwise direction. The reason is the way we build our model. We will explain that shortly. Okay, what we want to do now is, let's say for any vertex, let's say that's a chosen vertex. It can be any one of the remaining 6. What we are going to do is we are going to pair it up with the very next. Don't forget, in the remaining of the problem, we always assume we are doing the selection in the counterclockwise. Therefore, the very next vertex is a vertex in the counterclockwise direction, not the other way around. Okay, let's make that clear. What we want to do is we want to pair any chosen vertex for this triangle with the very next vertex that's kicked out as a pair. We call this a pair. Since we are going to select two vertices, let's make another pair. The dot is the chosen vertex, and the little circle is the kicked out vertex. That's the very next to the chosen one. And we make this a pair. And these two pairs accounts for 4 vertices, right? And we have another 2 vertex that got to be kicked out. All right, now we build a model of 4 objects. Let's call this a star. It doesn't matter, we just give it a symbol. Let's call this a star. And this single vertex a star, and this single vertex a star. Then the rest of the story is to select 2 stars so that we can place the 2 pairs, these 2 pairs, in the position of those 2 stars. For example, you can select the middle 2, or you can select these 2, that doesn't matter. Let's put the 4 stars here again. Once after we selected the 2 stars to place these 2 double vertices, then we can list these 6 vertices, chosen or unchosen, in a line. For example, the second and the fourth are the 2 selected stars. We will put it this way. Let's place all the vertices in there. This is the 6 vertices, right? Then we place these 6 vertices in this direction, in our counterclockwise direction, from this vertex all the way to here. That gives a way to select the 2 vertices for the triangle. One may wonder, does that satisfy this condition so that they have no common size? The answer is yes. Because first of all, since this vertex is kicked out, we only need to consider this one. Will any chosen vertex be this one? The answer is no. That is because of the way that we construct the pairs. When we construct our pair in this way, then the selected vertex can at most be this one. This is the last vertex that can be selected, right? Because if this is a dot, we always pair a dot with the very next circle. Therefore, this one got to be circle. So we are good. Then the question is, can these two selected vertex be next to each other? And in that scenario, we will have a common side, right? The answer is still no. Again, that's by the definition of such pairs. Since we pair them up with the very next vertex to be kicked out, even if these 2 pairs are next to each other, for example, this is a good example, right? Then these 2 dots are still separated by this circle. And let's make another example. Let's say these pairs are next to each other like this. Then still we see this is the chosen one, and this is the chosen one, right? And they were separated by this little circle. Therefore, we are always good. Okay, with this mathematical model, the question is, how many ways can we choose the 2 stars to place the 2 pairs? Then certainly we have 4 choose 2 many ways to select the 2 stars, or in other words, to select the 2 pairs. And then, don't forget, the starting vertex is a randomly chosen one. It can be any of the 8 vertices of the octagon. Therefore, we have 4 choose 2 times 8 many ways to select 3 vertices that are not adjacent. Good. Are we done yet? No. Look at this. I'll use a blue color. Let's suppose this point, this point, These two vertices are the chosen vertex, right? Let's label them as 1, 2, 3. And suppose 1 is the very beginning vertex. In that scenario, this 1 is count once, right? And when we let 2 to be the starting vertex, then this is also a good scenario, right? 1 can be count again. When we put 3 as the starting vertex, these 3 points can also be a good triple. Therefore, this vertex 1 is counted a third time. We know that all triples of satisfying vertices for this triangle can be counted 3 times. Then this number got to be divided by 3. This is the number of triangles that we can construct without duplication. Good. Then what is the probability? The probability for this one, the probability for this condition equals 4 choose 2 times 8, and then times 1/3, right? 1/3 is for this. Then this whole thing is divided by 8 choose 3, right? That's the total number of triangles we can construct from 3 randomly chosen vertices, regardless of the number of common sides. Good. So this equals what? This equals 4 factorial over 2 factorial times 2 factorial. Let's place 1/3 here, and then times 8. And the bottom is 8 factorial, 5 factorial, 3 factorial. Yes, the bottom is this. To simplify this fraction, we'll multiply 3 factorial on the top and on the bottom again. Now let's cancel this, these 3 factorials, and then let's cancel 5 factorial with this 8 factorial. So we have 6 times 7 times 8 left. On the top, we have 3 factorial. That cancels with this 2 factorial times 3, right? 2 factorial times 3, that's 3 factorial. Good. And this 2 factorial cancels this 4 factorial. We have 3 times 4 left. Good. So let's clean up. On the top, we have 3 times 4 times 8. We still have 8. On the bottom, we have 6 times 7 times 8. And that equals what? So 8 cancels 8. We break this 4 as 2 by 2. Then 2 times 3, that's 6. That cancels the 6. Okay, so the final solution is 2 over 7. But don't forget, this is not the probability for the original problem. This is only the flip side of the coin. Therefore, the probability for the original problem is 1 minus the p. That equals 5 over 7. Okay, let's browse up and take a look at the choices. Good. 5 over 7. Our answer is still D. Therefore, the two different methods, very different methods, give us the same solution. If you like this video, please subscribe the channel and thumb up. If you have questions, please comment.